Welcome to class 21. The last two classes, this one and the next one, are going to discuss instrumental variables regressions. These are specific type of techniques, quite new to what we've been doing so far, that are hopefully under certain circumstances going to solve some of the internal validity issues we mentioned in the previous class. Let's go back to our crops and war example. In last class, we basically said looking at the effect of crop yields on likelihood of civil war is going to fail the internal validity test on pretty much all dimensions. Remember that what we wanted to look at was the effect that crop yields may have on the likelihood of observing civil war in specific regions in the past. Specifically, we mentioned that simultaneous causality may be an issue here. Remember, we said, well, maybe crop yields have a positive impact on the likelihood of civil war. So it's positive in the sense that as crop yields are going to go down, it's going to make likelihood of civil war more likely. But it may also be that civil war itself has a negative impact on crop yields. Well, if the civil war kills about half of the population, you just have half many people working on the field. And so civil war may have a negative impact on crop yields. This would be a simultaneous causality bias. We also said that measurement error would be an issue here. This is because probably you're going to misreport crop yields in a way that has more measurement error in cases where civil war occurred. And this is because, in the year where you have a civil war, you're more likely to have not such great statistics. Maybe the people that are usually counting the yields are now going to war, and plenty of other reasons. If these are true and other possible issues are true, then we would not get that our expectation of ui given xi is going to be 0. This is going to fail, and we will get that is actually different from 0. And this is not even mentioning the fact that you may have omitted variables bias on top of all of that. Today, we're going to look at a technique that is actually, hopefully, under the right conditions, going to solve all these issues at once. All the threats to internal validity plus omitted variable bias, the typical kind that we saw a while ago, and that was the point of your assignment 1. These techniques are going to hopefully deal with that. So imagine that in your data set you have a third variable, and specifically this variable would be rainfall. So for each I, you would have some measure of rainfall. And say, because you went to primary school maybe, you have good reason to believe that rainfall is a determinant of crop yield. In case it's not obvious to you, on years where it's raining more or in areas where it's raining more, usually yields tend to be larger. But say also that you believe that whether or not it's raining, whether or not the rainfall is high, is completely unrelated and correlated with the likelihood of civil war. This means that you're going to have a data set in which you're going to have regions with high levels of rainfall on average, regions with low levels of rainfall on average. If you think that this is completely uncorrelated with civil war, but is absolutely correlated with crop yield. Again, areas where it rains are more likely to have higher crop yields, but are just as likely to have or not civil war. Then you could use this variable, rainfall, as what we're going to call an instrument for crop yield. And that's the question we're trying to ask here. Is there something we can do with rainfall variable that is going to help solve our estimation problem? And surprisingly, the answer is going to be yes. So, note that you can separate two sets of reasons why crop yields are going to differ across regions. One, rainfall. Second, everything else. In everything else, there's technological levels. Some regions are more advanced, and so some regions are going to be more productive than others. But some regions are just going to differ by rainfall. Rainfall, as you know, are going to have a positive impact on crop yields. If rainfall only has a relationship with civil war through its effect on crop yield, then it cannot be in the error term. In other words, rainfall only has an impact on crop yield, which itself has an impact on civil war. If this is the case, then rainfall is not in the error term. Remember what would constitute an omitted variable bias. It would be if rainfall was correlated with crop yield and a determinant of civil war. In here, what we're hoping, what we're going to use, is the fact that rainfall only has an effect on crop yield and not on whether people are going to war. If an area has more rainfall than another, I hope that this is not a determinant of whether they're going to civil war, except if the reason is that rainfall is changing crop yields across regions. Again, if it's the case, then rainfall is not a determinant of civil war and is therefore not in your error term. So, the correlation between crop yield and UI must be due to factors in the everything else category. So, if you have some sort of omitted variable bias here, it has to come from, again, technological differences across region. Maybe regions that have higher levels of technological advancement, say, also have higher levels of technology in war, and that makes them more likely to go to war, or the opposite. Maybe if you have higher levels of technological advancement, your yields are better and you're less likely to go to war. Okay, so these would be in the error term, but they are coming from the everything else category, not rainfall. Again, what we're hoping here is that rainfall has an effect on civil war only through its effect on crop yield. So could we somehow quantify the variation in crop yield that is due only to rainfall and define this as a new variable? If we can, then we're going to have a variable that is going to capture cross-regional variation in crop yield and that is not going to be correlated with UI. Again, if rainfall is only has an impact on civil war through crop yield, then it's not in the error term. If we have a variable that is not correlated with the error term, but has an impact on crop yield, then we're going to be in a very good situation because our expectation of UI conditional on that new variable is going to be 0. So Let's represent this mathematically and say first, we're going to look at an equation in which our dependent variable is what used to be our independent variable. Our dependent variable here is going to be yields, measured in, tons of whatever crops, it doesn't matter. But yields is now, in this case, our dependent variable instead of being our independent variable. And define Zi as a rainfall, you could think of it as average rainfall for region I. So, in this equation, we're having the effect of rainfall, average rainfall, on crop yields. Then, the sample regression line from estimating this model we would get would look like this. You're familiar with this, okay? So, abstract from the fact that this xi was in our previous scenario the independent variable. Now it's the dependent variable. If xi is here and is now our dependent variable, and I estimate this model, I can use my sample regression line to now predict x's. I'm giving you some z, you're multiplying it by pi hat and pi 0, and I'm going to predict an x hat. This is absolutely not new to you, except for the fact that now we call them x and z, to just keep track of the fact that our independent variable of interest, crop yield, is now here. And so z is now the rainfall. Later on, we're going to call that our instrument. But again, here I'm capturing the effect of rainfall on crop yields. Once I estimate this, I can then predict xi. Note that this everything else determinants of xi are in the error term vi. This is estimated by this xi minus x hat. So everything else is in the residual. So here, how I would like you to think about this x hat high. X hat high corresponds to variation across regions, that's why we have an I here, due to changes in rainfall and changes in rainfall only. Everything else that may be some omitted variable bias is not in there. So what regression would we want to use to answer our research question, which is still, what's the impact of crop yield on probability of civil war? Well, remember, we want to regress yi on a variable that is going to embody variation across region in crop yield, but is not correlated with ui. We want this expectation of ui given this variable to be 0. This is the first assumption of our regression models. We really want that, we need that, otherwise we're going to have inconsistent betas. Something we could do is run yi on xi hat. That's actually what we're going to do. And this method is called the two-stage least squares. In the first stage, we're going to regress xi on zi. Through that, we're going to get this estimated xi coming from the sample regression line. We're going to have a variable xi hat, which is coming only, so that is different across region i's, only through rainfall, which is really what we said we wanted in order to be uncorrelated with ui. Again, this method is called two-stage least squared because once you get this xi hat, then you can actually regress yi on xi hat. So Let's generalize this problem and solution. So say you want to estimate the effect of a variable x in general on a variable y, and you want to use a simple linear regression model like this. This one is super familiar to you now. Okay, say x is an endogenous variable. That's what we say, that's the term we use every time xi is actually correlated with the error term. So there's some sort of omitted variable bias or plausibly simultaneous causality. Every time expectation of ui given xi is different from 0, we're going to talk about xi being an endogenous variable. Say there exists an exogenous variable z that you could use and that is actually uncorrelated with error term. In our example, this was rainfall. Why is rainfall exogenous? Because unless you're some kind of wizard, rainfall locally does not depend on anything you're doing. Rainfall is really something that is completely exogenous to everything people are doing on the ground. To use a two-stage least squares, you first are going to regress what you're going to call the first stage regression. In this first stage, you're going to regress the endogenous variable on the exogenous variable. In the second stage, you're going to use the predicted xi coming from your sample regression. And so, as we had before, you're going to get a predicted xi that is going to get only the variation through zi. If zi is once more truly uncorrelated with ui, not vi, ui, then you're going to get a satisfying instrument. Both those regressions are using the OLS model, but the resulting estimator beta 1 is not the OLS estimator we derived in class 2. So recall that beta 1 hat is the sample covariance between x and y on the sample variance of x. It turns out that the beta hat 1 that you get from two-stage least square, so that's the one coming from regressing yi on xi hat, okay, so that's the one you get from the second stage, is actually the ratio of the sample covariance between z and y on the sample covariance between z and x. To see this, and see why we're going to have a consistent estimator of beta 1, consider the following. So consider the covariance between zi and yi. So zi, remember, is our exogenous variable. In our example, this was rainfall. Yi is our dependent variable of interest. In our example, this was probability of war. So you can express yi as being beta 0 plus beta 1 xi plus ui. This is the regression that we all know about. The equation, we all know about. Now, the covariance between zi and beta 0 here, beta 0 is a constant, and the covariance of a random variable with a constant is simply 0, so you don't have to care about this. The covariance of zi plus with xi is here, and the covariance between zi and the error term is here. But what did we say about the covariance of zi with ui? Well, we said under the right condition, it should be 0. Under the right condition as well, the covariance between zi and xi should be different from 0. Think back on our example. I want rainfall to actually have an impact on yields. Otherwise, my exogenous variation is useless. If I think of an instrumental variable Zi that is not correlated with my supposedly independent variable, the endogenous independent variable of interest, then I have a problem here. Okay, so I want this covariance to actually be different from 0. If it's the case, then my beta 1 is going to be expressed as, and this is coming from the fact that this is 0, and you can take this to the other side. And so beta 1 is the covariance of Zi with yi on the covariance of Zi with xi. As usual, I do not want you to learn this by heart, even though by now it's everything open book. But I want you to understand what are the components here. We said we wanted an exogenous variable Zi that is exogenous, truly exogenous, such that the correlation between Zi and ui is 0. This is when this term here goes to 0. Note, I cannot prove that. I just hope that I found a Zi for which this is actually true. This condition again, in our example, meant rainfall has no impact on the probability of war except through its effect on crop yields. Note that it's not necessarily true. I'm kind of setting something here. It's not exactly true, or potentially not true. Maybe, just maybe, rain is actually correlated with the probability of war. Say you're in a region where rain is so high that it destroyed houses. People get very mad, and some sort of civil war ensues. That's a possibility. But let's just assume for now that is actually true for example, and anyway, we're now looking at a broader example. So for a good instrument, this should be true that the covariance of Zi with ui should be 0. Second, I actually want that the covariance of Zi with xi is different from 0. I want to make sure that my exogenous variable actually has an impact on xi. If it's not the case, then my prediction of xi is just going to be 0 everywhere. Okay, I hope that makes sense from this part. If there's no correlation between z and x, then this parameter here is just going to be 0. What am I going to predict? Given some zi, 0 everywhere. So I'm no longer predicting anything here. And when I regress yi on xi hat, I'm just predicting how y is changing as x is 0 everywhere. Obviously, I have nothing. So these are the two things you need for an instrumental variable in a two-stage least square estimator. So why is this consistent? As the sample size becomes arbitrarily large, the sample covariance between z and y over the sample covariance between z and x will get increasingly closer to the actual covariance in the population between z and y over covariance of z and x. And this will be true as n increases. This will get closer to this with probability approaching 1. This means that the beta hat two-stage least square will be close to the true beta 1 with probability approaching 1. Stated differently, beta hat two-stage least square is actually a consistent estimator of beta 1. So I'm going to state again the conditions for a valid instrument. This is absolutely key. a researcher that is using an instrument in his research program, in his research paper, is actually going to spend a lot of time defending that he has a valid instrument. Actually, the whole point of the paper is whether or not he has a valid instrument. If his instrument is not valid, well, then it's not worth anything. So, as I said before, we want two things. We want the correlation between Zi and Xi to be different from 0, and we want the correlation between Zi and Ui to actually be 0. The first condition, a valid instrument variable or instrument Z must satisfy both of these conditions. Okay, so again, you're going to say you have a valid instrument if both those conditions are satisfied. Spoiler alert, there's no way you can prove that the second condition is satisfied. You can never prove that the correlation of your exogenous variable, again in our example rainfall, is actually uncorrelated with the error term. This is because, by definition, you don't know the full list of potential variables in the error term, and so you can never prove that this is true. You can only suggest that this is true. The first requirement here is going to be the relevance condition. An instrument is relevant if the correlation between that instrument, that exogenous variable, with the endogenous variable is different from 0. And so let me say that again in the context of rainfall. Rainfall is a valid instrument if it changes crop yields. In this case, it's fairly intuitive. I think you know that. I think you know that when it rains more, the yields are better, especially if you're looking in the past where technology was really low, and so yields were highly dependent on rainfall. So this is the first condition. If the first condition is true, that is, if you find an actual correlation between Z and X, if you find an actual relationship between rainfall and yields, then you can go to the second condition, which is called the exogeneity condition or the exclusion restriction. What does the exclusion restriction say? It says mathematically this, that Zi should be uncorrelated with Ui. What it says, again, if you're a researcher and you're proposing a given instrument, it means that nobody in the room can say, look, rainfall is going to impact the probability of war through a mechanism that is not crop yields. If what this person is saying is true, then it violates the exclusion restriction. Again, the exclusion restriction is really about your instrument Z should only impact probability of war, or the Yi of interest, through its impact on X. If you can come up with a story that is plausible, that says rainfall or your instrument is going to impact probability of war or any given Y through something different than crop yield, then you violated the exclusion restriction. Now, as I said, you can never prove that you're respecting exclusion restriction such that you're going to defend the use of an instrument and claim that it is valid by listing the obvious ways by which you may think the exclusion restriction is not respected. But if nobody basically can come up with such a mechanism through which Zi may impact probability of war through something else than Xi, such that this would be different from 0, then it's more likely that you have a valid instrument. We can also show that this beta 1 hat is normally distributed in large sample. You see that the formula here is actually one that is kind of familiar to you, except for this part maybe. But the idea is that because it's going to be normally distributed, it means that we can make inferences the same way we're doing it with beta OLS. Okay, so the beta hat from two-stage least squared also have the same interpretation in terms of significance when we're making inferences. In Stata, which sadly we can no longer use, if you were to use the two-stage least square command, Stata would calculate for you the standard errors following this formula. You would still have to say whether you want robust or clustered standard errors the way we mentioned in previous classes. But if I am showing you the result in Stata of a beta two-stage least squared instead of being a beta OLS, you would interpret the p-values and the standard errors and so on exactly in the same way we're used to in the OLS. This finishes the first part of class 21.